Hello everyone, this is John Buck back with another discrete time linear systems video. And in this video we're going to talk about the continuous time Fourier series and the properties of that Fourier series. So particularly we're going to look at the case where if I have some time domain signal x of t whose Fourier series is a of k, which if I write that out more precisely, this is the same as saying that x of t can be written as the sum as k goes from minus infinity to plus infinity of a sub k e to the j k omega naught t. Or more conceptually, we're saying that x of t is a periodic signal with some period t that we can write period capital T that we can write as a weighted sum of exponentials where the frequencies are harmonically related. Right? So we're going to assume that we have all of these signals have the same period t. That's important. They all have the same period, so they all have the same fundamental frequency too. Right, and that omega naught is 2 pi over t. Right, so we're assuming that just as I can write this for x, that there are similar sums we can write for y to b and w of t to c of k. Right, that each of these on the right-hand side is a different Fourier series for different time domain signals. And what we're going to look at today is when I can write relationships between the signals in time, what does that imply about the relationships between the Fourier series coefficients? Or vice versa. If I define b of k in terms of a of k, what does that tell me for certain operations or certain properties? What does that tell me about a relationship between x of t and y of t? Okay, so that's our main theme for today. So just reiterating, if I write y of t in terms of x of t, what does that tell me about how to write b of k, the Fourier series for y of t, in terms of x of k, the Fourier series for x of t? In terms of a of k, rather, which is the Fourier series for x of t. So how do those relationships build? And what we'll find as we go through these is at the conceptual level, if you just use words without equations, they're pretty much all the same conceptual relationships that we saw in the discrete time class. So you have a strong foundation to build on here. We just have to get used to the slightly different details when things are written in terms of continuous time. And the other big difference in the Fourier series now is that the sum is infinite, right? That I have an infinite set of harmonics, not just one period's worth of harmonics that I need to use. So let's see how this works on the next page. All right, so the first one is what if w of t, my new signal, is a weighted sum of a times x of t plus b times y of t, where these two are constants. And again, it's important, so I'll reiterate it, that these have the same period. So to help you refresh your memory of these things, when we say these have the same period, but also, go ahead, I'm going to encourage you the whole way through this video, as I state each property, to pause for a minute and at least try to think conceptually about what you expect to be going on in the opposite column as we go through filling these in. So again, from what you remember the Fourier series, if I have one signal is a weighted sum of two other signals, when I scale and add things in time, what happens to the Fourier series if they all have the same period? Pause and think. Right, that the new series is also just the same property. Right, that linearity, that's not working. What's wrong with it? Oh, there it is. That linearity holds for the Fourier series, so I have the same adding and scaling of the Fourier series coefficients, right? So that the coefficients for w of t, the c sub k's, are a times the a sub k's plus b times the b sub k's. Moving on to the next one, if I shift a signal by t naught, delay it by t naught in time, what do you expect to happen in the Fourier series? Pause and think. Okay, now that you're back, right? The same thing that happened in discrete time, which is a shift in time is multiplying by a complex exponential in frequency. So when I do this, the new Fourier coefficients will b sub k times e to the minus j k omega naught and t naught. Instead of just a general t, I have the amount of the shift appearing here in the exponent times the a sub k. So I have the same a sub k I had before multiplied by this complex exponential, which is due to a shift in time. Thinking in the other direction, what if I shift the Fourier series coefficient? So what if I take a sub k and shift it by m on the Fourier side in frequency? what do you expect to happen in the time domain? Pause and think for a second. Right, this is also multiplying by a complex exponential. So in this case, the new signal y of t will be multiplied by a complex exponential as well. So that shifting in time causes multiplication with a complex exponential in the Fourier series, and vice versa, shifting the Fourier series multiplies by a complex exponential in time. And together, these two properties are sometimes called the shifting or modulation properties, because modulation is what we call shifting things in frequency, or is a very common kind of modulation. Maybe the original kind of modulation is shifting in frequency. All right, how about this old friend? If I take two signals and I convolve them in time, again, where I'm using star for the convolution, I can write the integral out if it makes it easier. Pause and think for a second. Convolution time is, right, multiplication in frequency. So that I have ck is equal, I go k by k, multiplying the corresponding Fourier coefficients, and then there is just a scaling factor of t to make sure the numbers all work out here. So convolution in time, multiplication in frequency. I think I've heard that one before, right? That should be familiar to you. How about this? This is a convolution sum in time. If I look at the Fourier series coefficients, I say I can pretend those are a sequence, right? They are a discrete sequence in k, so I can convolve them just like I convolve signals. I can convolve in frequency just the way I convolve signals in discrete time. What do you think happens when I convolve on the Fourier series side? Right, I multiply in time. So by convolving the two Fourier series A and B, I multiply the corresponding signals x and y. Okay, let's move on to the next page. There's still more properties to come. Another important property for continuous time, because we often build systems by implementing differential equations or systems that approximate differential equations, is what happens when I take a derivative in time. We talked a little bit about taking a derivative in frequency once or twice last term, but because t is continuous now, we can actually take a derivative in time, not just delays. What happens is that we multiply by j k omega naught. And what about the other direction? If I say, well, what happens if multiplying by j k omega naught is taking a derivative? What if I do it the other way? What if I divided by j k omega naught? What sort of the opposite of a derivative would I expect? Pause and think for a second. Right, if I do the opposite, you could almost imagine dividing both sides here by this. I'd say a is like this. Well, that's confusing because I'm using a's and b's, so forget I said that. But what I'm doing here is I'm taking a running integral. So in this case, if I take b to be 1 over that, 1 over jk omega naught times ak, that's equivalent to saying I'm going to say y, the corresponding time domain signal, is the integral up from time. I got the wrong upper limit there. The integral of x of t from minus infinity to t of x tau d tau. So if multiplying by jk omega is a derivative, to integrating is dividing by it. What about if I take the real part of a signal? Remember back from what we saw last term. If something is real in one domain, what are we looking at in the other domain? Pause and think. Right, we're saying it's the even part. Right, so I take the even part of a sub k, which is the same way I did it last term. I take the a sub k, I flip it in k, and take the conjugate and add it. So that's the conjugate even form. Similarly, if I take, what do you guess? If I take the imaginary part in time, what do you think is going to happen? Right, it's the odd part. Right, so for the odd part of a sub k, I take a sub k, I flip it in k and take the conjugate and subtract the two from each other. And so between the even and the odd parts, I've got both parts of the signal, the real and imaginary. This does lead to some other properties we could say. So, for example, if a of k is real, if I have a real Fourier series, that tells me x of t is conjugate even, which means it's equal to, if I flip it in time and take the conjugate, I get the same thing. Another one we'll see is if x of t is real. Right? We deal a lot, almost entirely really, actually in this class, with real time signals. That tells me a sub k is conjugate even. Right, which says that a sub k is equal to the conjugate of a sub minus k. Okay, and so these are the two sides of the fence that we often see coming up very often, time and Fourier series. There's one last thing that sort of covers both sides of the fence, which is Parsival's relationship. Pause for a minute, see if you can remember conceptually, what does Parsival's relationship say? Okay, now you're back. What Parsival's relationship says is that the energy in a signal is the same whether I think about it in time or frequency. Or in this case, it's the average energy per period for the periodic version. So right now, what that says is that I've got 1 over the integral over one period of the magnitude of x of t squared dt. This is the one place where I get out my eraser and I sort of break the wall. All these other ones are sort of, we have these double arrows saying, not that these two things are equal to each other, but they correspond to each other. If I do this derivative in time, I multiply by jk omega in frequency. If I shift in time, I multiply by a complex exponential in frequency. Parseval's theorem is the only one where we actually break the line and erase it and say, if I compute this is the average power in one period of the signal, that is exactly equal to the sum of the squares of all the Fourier coefficients. Right, so this is the one place where I actually have an equality between the time domain signal and the Fourier series is through Parseval's theorem. Okay, so that's a quick review of the main properties we're going to use this semester. Again, conceptually, they're all the ones you've seen before are the same. The derivative and integral are a little new for us. We didn't use those in discrete so much. But all the other things, shifting in one domain is a complex exponential in the other. Multiplying in one domain, convolution in the other. Real and even in one domain, even and real in the other. Odd in one domain, imaginary in the other. All those things line up. And even Parsival's is conceptually the same. So I'm going to stop this video here. And the next video I'm going to go on and show you an example of how we can use those to let us be smart and lazy engineers, which is to find the Fourier transform of a new signal very directly from one we already know, rather than just doing the integral from scratch. Okay, that's all for this time. See you in the next video.